Okay, welcome back. We have just defined what the dimension of variety is. So now we have varieties, we have dimensions, so we know what dimension 1 means. Now we actually call those curves. So I'm going to write here a definition which says that projective variety, or a curve, is by definition projective variety of dimension 1. Okay, so we just have an example, a couple of examples back there of projective varieties of dimension 1. Now, we also want to know when curves are smooth, right? But I'm not going to define a smoothness for an arbitrary variety. I'm just going to do it for in a particular case. So let C be a curve. I might as well use the terminology I just defined. And let C be a curve and defined by f of x, y, z equals 0. Then C is singular at P if and only if the following conditions happens: that the derivative of f with respect to x and evaluated at P, and the derivative of f with respect to y evaluated at P, and the derivative of f with respect to z evaluated at P, all of them vanish. Okay. If you are slightly uncomfortable about taking derivatives and over fields that might not be as finite fields and so on, if that's not very natural, you can actually do this completely, so equivalently, you can do this completely algebraically, and in fact, it's one of the problems that I suggest in the first homework problem. So if we let MP be the following set of functions in the function field, actually function in the affine coordinate ring, that vanish at P, then it turns out that, and V is a variety, then P in V is non-singular if and only if the dimension as a k-bar vector space of MP over MP squared equals the dimension of V. Okay, so you can do it that way too. And again, it's an exercise in the homework set. Let's do an example. What can we do? Let's look at our favorite curve, just to check that is smooth. Notice, by the way, that the definition of a curve says projective, and that when we say singular or non-singular, it refers to curves. So in particular, it refers to curves as projective varieties. So we need to check, whenever we check singularities, we need to check in all charts, basically. So we need to know that it's non-singular as a projective variety. Okay, so let V be this curve. Okay, and then we just compute. So let's compute the derivative. So I'm going to take f. So it's given by v, with v being that polynomial zy squared minus x cubed plus z squared x. Okay, So let's take the derivatives. So fx with respect to x, what we get is minus 3x squared plus z squared, right? With respect to y, what I get is just 2zy. And with respect to z, what I get is y squared plus 2zx, if I did that right. Okay, so now let's argue. So what happens if all of them vanish? Well, if they vanish, so f of x being, or f of y rather, f of y being 0, that tells me that, well, either z is 0 and that's why it vanishes, or z is non-zero and then y is the one that vanishes. So there are two options. If z is 0, it turns out that there is only one point on my curve. Okay, so together with the definition, see, if z is 0, then x must be 0, and then the only other point, the only point there is y equals 1. Okay, so there's then p has to be 0, 1, 0, but at 0, 1, 0, let's see, the f of z, the third derivative, does not vanish. Okay, so it is non-singular at p, at that point at infinity. So then we must have that z equals 1, or z is non-zero, but since we're in projective, we can assume that z is 1, and if z is 1, then y must vanish. And if y vanishes from f of z equals 0, I can deduce that that x must vanish also. But then from f of x being 0, then we also deduce that that we have z equals 0. But then p cannot be 0, 0, 0, and we've reached the contradiction. So the result is, yay, there is no singular points. So we say that it is smooth. Okay. You have to be very careful, as I said, with the coordinates, that if you're checking a curve, to make sure you are checking it in projective. So for example, if you take this curve in A2 and over the affine plane, it's very nice and smooth. It's some curve that every calculator student would recognize, and it's smooth. But it turns out that it has a kink, it has a cusp and at infinity. So this is actually singular as a projective curve. Okay, so I'll leave that as an exercise. Just check that there is a singularity at infinity somewhere. Okay, so that doesn't count. This is a cubic, dimension 1, but we do not have the smoothness for that one, so it is not an elliptic curve. Will not be an elliptic curve in our definition. All right, very good. So what else do we have? So I'm going to now move to define the concept of the local ring of V at P. So we're going to start thinking about functions. And first of all, you can think about functions locally at a point. So the local ring, let, again, V be a variety. And P a point on my variety. The local ring of V at P called KVP is the localization of the affine coordinate ring at MP, which I defined before. So then the local ring is simply functions in the function field of V such that F are quotients of functions f and g, with f and g in the affine coordinate ring, because this is part of the field of fractions, but g does not vanish at P. Okay, we say that F, like that one over there, is regular at P. Okay, and then what we want to do is actually define more generally regularity of points in maps between projective varieties. Okay, so we're going to do that next. All right, so now let V1 and V2 be projective varieties. And we're going to define what is a rational map. A rational map between V1 and V2 is a map of the form V from V1 to V2 that sends a point to a point F0 P dot Fn of P in V2 where these F0 through Fn are in the function field of V1. So that is the definition of a rational map. Okay, so this is a rational map between V1 and V2. And what we want to say is, what does it mean for phi to be, for phi to be regular at a point P? I'm going to do that in the next page, so I have also some room for an example. So let's write definition and leave some room for examples over here. Okay, so definition, a rational map, like before, is regular at P in V1 if there is some function g such that, well, each g times fi, remember the definition of phi in the previous page, so phi had several components given by rational functions by functions in the function field f0 through fn. So g times fi is regular at P. So there is no vanishing at P in the denominator of that function. And two, for some I, we have that g times fi evaluated at p does not vanish. So there are two problems that could happen, that a function might not be defined at p. For example, it could be that everything vanishes at p, and then that is not a point that is projective, or it could be that one of these has a pole at 0, and those two things would make it not be well defined. So, but however, because of the projective definition of the map, we can scale the whole vector by some other function, some other constant, and then see if that helps. So what is happening here in the definition of regular is allowing for that there might be another function that I can multiply all the functions fi's by that make the function regular at p. So but let's just finish the definition here, and then a rational map is regular at p. That's what we define there. And then I'm going to say that if phi is regular at all p in V1, then we say that phi is a morphism. Okay, so let's go through an example together of a map. So here is a rational map. I'm going to go from I'm going to think of two. I'm going to go from V1 to V2. My V1 is going to be just the variety given by zy squared equals x cubed plus z cubed. Okay, and V2 is just going to be P1, and the map itself is going to send a point to xz. So it's basically forgetting about the y coordinate. Okay, so that's what phi does. And you see that what happens when x and z are 0, which happens because we have a point 0, 1, 0 in there, that would not be defined. So I'm going to define it. I'm going to extend it by sending 0, 1, 0 to 1, 0. And I want to check that this map is actually a morphism. I want to see that it's regular at 0, 1, 0. Okay, so from the definition of the map, so I get the target is just xz. Okay, what I'm going to do is multiply my g, as in the definition, is going to be x squared. So I'm going to multiply both functions by x squared, and I get x cubed z x squared. Okay. Now I'm going to use the definition of the function, of the definition of the variety V1 by the definition. I can actually use that definition to replace x cubed by zy squared minus z cubed. Okay, and then you see that I have a multiple of z everywhere, so I can actually divide by z everywhere, and now I get y squared minus z squared comma x squared. But you see now these two functions, these two formulations of phi are equivalent, but the latest one, when evaluated at 0, 1, 0, I get what do I get? I get 1, 0. Okay, so that works. There is a value now for 0, 1, 0, where before it was undefined, and it matches the way I defined it myself at that point. Okay, so then we say that that phi map is regular. Very good. Let me give you one more example, maybe here, of another map. So I can go from, let's take V1 to be 3y squared equals x cubed plus 1, and V2 to be y squared equals x cubed plus 1. So there is a map between V1 and V2 that sends xy to x comma square root of 3 times y. This map is not defined over Q. So this map itself, because of the definition of the polynomials, because of the field of definition of this is not defined over Q, but is defined over Q adjoint the square root of 3. Okay, so this map is actually a morphism, and there is also an inverse. There is clearly an inverse function that goes the other way, and when that happens, then we say that the two are isomorphic, that the two varieties are isomorphic. So let me write that down. So we say that V1 and V2 are isomorphic if there are morphisms, and that's important. They have to be morphisms. Phi, they have to be morphisms, not just rational maps. And psi, V2 to V1, that are inverses of each other. So that phi composed with psi and psi composed with phi are the identity on V2 or V1 respectively. Okay, and indeed, this example shows that these two varieties are isomorphic, and that is a very important example of an isomorphism, that if this is an elliptic curve, and this is what we called a quadratic twist of V2, and vice versa, V2 is a quadratic twist of V1. Those are very important in the theory. We'll get back to them much later in the class, and yeah, so the point is that these two are isomorphic over Q adjoint the square root of 3, but not over Q. There is those are not isomorphic over Q, but the isomorphism happens over Q adjoint the square root of 3. Okay, so I think I'm going to stop here for today. I think I'm out of time, and I will continue next time. Next time, we'll start with more of the theory of algebraic curves and start talking about order of vanishing and about divisors, which will be all the tools we need to state the Riemann-Roch theorem. All right, very good. See you next time.